In this video, we'll talk about characteristics of exponential functions. So the basic form is f of x equals base b raised to the power x. So examples of this would be f of x equals 4 to the x, or y equals 2 to the power x. So these guys that I just listed as examples over here. So down here below this, I have just a little sketch of kind of a basic exponential function. This is an exponential growth function, by the way. So where the base b is greater than 1. Exponential decay would be getting smaller as we go to the right as x increases. So for either of those, but specifically here I'm looking at this graph of exponential growth. Remember that our domain, which is our x values, is all real numbers from negative to positive infinity. And if we don't have any vertical shifts up or down from this basic function, the range goes from 0 to positive infinity. Remember, I'm using that rounded parenthesis at 0 because we have this asymptotic behavior where that red dashed line is. That's our horizontal asymptote, y equals 0. Also, notice that these basic functions pass through the point 0, 1. Always passes through the point 0, 1. That's because, for example, if we look at our function f of x equals 4 to the power x, if we want to evaluate the function at f of 0 equals 4 to the power 0, 4 to the 0th power equals 1. When x equals 0, y equals 1. All right, these functions are one-to-one functions. They have an inverse that's also a function. Remember, you can apply the vertical line test to confirm that you have a function, and then the horizontal line test to confirm that the inverse of your function would also be a function. So this is a one-to-one function, all exponentials are. The graph approaches but does not touch the x-axis. That's this asymptotic behavior, so the fact that we have an asymptote. For exponential growth functions, as x approaches negative infinity, so heading this way, f of x, your y value of your function, approaches 0. And the horizontal asymptote is the equation y equals 0. Remember, horizontal asymptotes are always in equation form. Y equals a number, in this case y equals 0. For exponential decay functions, which would, I'm just going to do a real quick sketch. So they would look, sorry for that. Wow, that's a terrible sketch, but pretend like that looks like an exponential decay function. As x approaches infinity, so as x is increasing, going to the right, f of x also approaches 0, and the horizontal asymptote would again be y equals 0. All right, so looking at some other examples of functions, remember before we looked at our function f of x equals 2 to the power x here in example number 1. We got this xy table, we graphed this function. So kind of riffing off of this basic function, we're going to transform that function a little bit. So in example number 5, we want to graph f of x equals 2 to the power x plus 1 minus 2. So in order to graph this, I'm going to use my y equals button on my graphing calculator. So over here I'll hit y equals, and then I'll go ahead and graph that function. So base 2, caret key, raised to the power x plus 1. And depending on your calculator, make sure that that x plus 1 stays in the exponent. Right now I can see that it's a superscript, but if you have an older calculator, you might need to put parentheses around your exponent above the 8 and 9 key. Those are your parentheses. In this case, I'm going to use the right arrow to get out of the exponent and then type my minus 2. And we'll go ahead and graph that. All right, so just looking at the equation before we actually look at the graph, the transformation that I would expect from this, in my exponent I have that x plus 1. This is going to create not a right but a left-hand shift by 1 unit. So left 1, a shift left 1. And then this minus 2, I would expect that to create a vertical shift down 2. So remember, those horizontal shifts are kind of the opposite of what we might initially think. X plus 1 creates a shift to the left 1. The vertical shifts are a little more intuitive. The minus 2 creates a vertical shift down 2. All right, so from that initial function that we had, remember that typically our exponential functions, the nice basic vanilla exponential functions, go through the point 0, 1. If I shift 0, 1 to the left 1, that puts me over here, and then down 2 puts me here at this point, -1, -1. So I can see that this new function goes through -1, -1. And by the way, to pull out these points that I plotted, remember that we can use the trace key. So that's a good way to pull out additional points that you want to plot. So here in my calculator, I hit trace. I can type in my x values. So -3, for example, gives me my y value of -1.75. That -1 for x produces a -1 for y. All the way down here at the bottom, if x equals 2, y equals +6. So I plotted those points and went ahead and connect the dots for my nonlinear function, that curved function. The domain of any exponential function, -infinity to +infinity, those are our x values. And then the range here, typically, if we don't have any shifts, any vertical shifts, remember that our range is typically from 0 to infinity, but we had a vertical shift down 2, so our new range is from -2 to infinity. So that vertical shift affects our range. Also, we can see for our graph, as we're going to the left, as x approaches -infinity, f of x, which is our y value, our y values are petering out at -2. They're approaching -2. So as a result, our horizontal asymptote is y equals -2. Horizontal asymptote is always a full equation. And if I want, I could go ahead and draw my dashed line. Here at y equals -2 to illustrate that horizontal asymptote. Okay, over here for number 6, we want to graph f of x equals -2 raised to the power x minus 1. So in my calculator, I'll go to y equals, clear that out. Here's my negative key, so -2 caret raised to the power x. I'll use the right-hand arrow to get out of that, and then type my -1. Hit my graph, and we can see we have a reflection of that exponential function. So, looking at our transformations, this negative out in front changes the signs of our y values, so that results in a reflection about the x-axis. So reflect across the x-axis. And this -1 is a vertical shift down 1 unit. All right, so remember our basic vanilla exponential functions pass through that point 0, 1. So if we think of taking our initial point 0, 1 and reflecting that about the x-axis, that puts us at 0, -1. Shifting it down 1 further point puts us at that point 0, -2. And again, we can pull out all of these points that we have in the xy table by using our trace function in our calculator. So if I type -2 for x, that gives me -1.25 for y. 0 for x gives me y equals -2. And then that final point at the bottom, x equals 2, gives me y equals -5. I plotted all of those points and connected the dots. Oops, let me stay on purple. All right, the domain is always -infinity to +infinity. The range, now this is interesting. Usually we have the range from 0 to infinity. We've reflected our graph across the x-axis. So that's going to take us from 0 down to -infinity, and then further, the shift down another 1 unit takes us from -1 down to -infinity. And of course, we write the lowest number, or -infinity in this case, first. So we're going from -infinity up to a maximum of -1, rounded parenthesis there. As x approaches -infinity, as our graph heads to the left, we can see that our graph is approaching, our y value is approaching -1. So f of x approaches -1, horizontal asymptote, y equals -1. right, and on the next page, we've just got a few other examples of these exponential functions. Y equals 3 to the power x. Notice that it passes through the point 0, 1. Y equals 6 to the power x passes through 0, 1. Y equals e to the power x, again passes through 0, 1. And y equals e to the power negative x, this is a decay function. The others were growth functions. Again passes through 0, 1. So reminder that e is a constant, just like pi is a constant, an irrational constant. So it's equal to approximately 2.72. I wrote down here approximately 2.718. And I'm going to hit second quit. If you forget that on your calculator, under this natural log, this ln key on the left side, about halfway down, you see a teeny tiny little e to the x. If I hit second and then my ln key, that puts e up on my screen, and it's expecting an exponent. So if I hit 1, there's my constant. All right, so e is a base just like 2 is a base, or 7 is a base, or 3 is a base. E is a number, it's just an irrational number, but it's a number, it's a constant. All right, so if we want to look at the graph of f of x equals e to the x minus 4, I can go into y equals, hit second, and then the ln key to pull e up on my screen, put x up in the exponent, hit my right arrow, and then type my minus 4. And then look at the graph. So we've already reproduced the graph for you here in the notes. You can, of course, use the trace function if you wanted to pull out individual points. Notice that the domain is still negative infinity to positive infinity. The range, remember that typically for a basic vanilla exponential function, the range would be from 0 up to positive infinity. We have this shift, vertical shift down 4. So that means our new range here is from negative 4 up to positive infinity for our y values. Our y-intercept, if it had just been f of x equals e to the x, like it is up here, it would just be 0, 1. But because we shifted down 4 units, that puts us at 0, negative 3. As x approaches negative infinity, f of x approaches negative 4. And that means our horizontal asymptote is the equation y equals negative 4. So we can see that dashed line right there for our horizontal asymptote y equals negative 4.